Ms. Stevens. If you're studying functions and want to learn about identifying domain and range, you're in the right place. This episode will focus on identifying the domain and range of a function given by an expression, table, set of ordered pairs, or a graph, and using set and interval notation to identify the domain and range. I'll start by providing a short lesson and then walk through a few sample problems. Let's get started. First, a few definitions. The domain of a function is the set of values that we are allowed to plug into our function. This set is the x values. The range of a function is the set of values that the function assumes. This set is the values that the function outputs after we plug an x value in. These are our y values. Let's take a look at an example. Find the domain and range given the ordered pairs or table below. So, to find my domain, I'm just going to list the x values. And in this set of ordered pairs, we have -3, 0, and 3. To find the range, I'm just going to list what y values we have. We have 9, 0, and another 9. We don't need to write it twice. So, that's my domain and range for a set of ordered pairs. How about a table? In this table, we have units and total cost. X values are our units, y values are our total cost. So again, we're just going to make a list. The domain, 2, 3, 5, and 10. Those are our units. And the range, I'm not going to put the dollar signs, but I'll write 20, 30, 50, and 100. Again, domain, list your x values, range, list your y values. Pretty easy. So how do we find the domain and range of a function in an equation form? Well, we're going to find the ordered pairs, we're going to plot points, and we're going to complete the graph. Example 2. Determine which x values can and cannot be evaluated in the function. So f of x equals the square root of x minus 3. So to get a sense of what works and what's not going to work as inputs, we're just going to pick a variety of numbers and plug them in. So positives, negatives, 0, as well as any big numbers and any really small numbers. So the first one I'm going to try is 0. If I take 0 and plug it in for x, I get 0 minus 3 is -3, and I can't take the square root of -3, so 0 doesn't work. How about a bigger positive number? How about 4? Okay, I can take 4 minus 3, that's 1. The square root of 1 is 1, so that works. How about a negative number? -2? -2 minus 3 is -5. I can't take the square root of -5. So can't plug in 0, I can't plug in -2. And the reason why is because I get a negative underneath the radical. So what if I just say x minus 3 has to be greater than or equal to 0? I can take the square root of 0, and I can take any number bigger than the square root of 0. So what do I get when I solve this? X has to be greater than or equal to 3. Well, that makes sense because 0 didn't work and neither did -2, but 4 did. 3 would work. 3 minus 3 is 0. The square root of 0 is 0. And any number bigger than 3 would work. So as long as I plug in those bigger numbers, those work. I want to take a quick peek at this function just to see what it looks like. So I can see when I plug in 3, I get 0 on this green graph here. And then as I keep plugging in numbers that are greater than 3 for x, I get y values. Y values are going to go up and up and up because I'm going to take the square root of larger and larger numbers. Okay, let's try another one. H of x equals x cubed minus x. So again, I'm just going to plug in some numbers. How about 0? Well, I can cube 0 and get 0. Minus 0, still 0. That's not a problem. How about a positive number? 2. 2 cubed is 8. Minus 2 is 6. That doesn't appear to be a problem. I could keep plugging in bigger positive numbers. How about a negative number? -2. -2 cubed is -8. Minus -2 is +2. Negative 8 plus 2 is negative 6. I can keep plugging in bigger negative numbers and I don't think I'll have a problem. I could do fractions. That's a little bit messier, but it should still give me a real number. If I plug in 1/2, I can cube 1/2. It's 1/8, and then subtract 1/2. So I'll get 1/8 minus 1/2 is my corresponding y value there. I can do that with positive numbers, negative numbers. I don't see any issues with plugging in any x values. So I think all x values are okay here. All right, let's take a look at that graph. So that's a cubic. Looks like I can plug in anything I want. If I plug in bigger positive x values, I get bigger positive y values. If I plug in more negative x values, I get bigger y values out. So I can plug in anything I want for x. One more. Y equals 1 over x. Well, I know fractions, and I can't have a denominator equal to 0 in a fraction. So the only way that's going to happen is if x equals 0. So I know that's bad. But what about anything else? Well, I can plug in positive numbers. If I plug in 1, I'll get 1 out in return. I can plug in a 2. I'd get 1/2. Can do the same thing with negative numbers. Negative 3, I'll get out negative 1/3. Can keep plugging in bigger negative numbers, bigger positive numbers. I can plug in a fraction, plug in 1/4. 1 divided by 1/4 is 4. That's still okay. So everything besides 0 seems to be okay. Let's take a look at that graph. Yep, I get a vertical asymptote at x equals 0, so that's why that doesn't work. But it looks like everything else greater than 0 or less than 0 gives me a y value. I've been using the Desmos graphing calculator emulator to visualize these functions. This is a free app to download. It's fairly intuitive to operate, and it's a nice standby when you don't have a graphing calculator handy. I'll be using this app for most graphical demonstrations, but I highly recommend investing the time to become proficient in whatever graphing calculator is approved for use in your class. As we just experienced, you can't always plug whatever you want in for x. With many functions, not every real number is going to be a member of the domain or the range. So if we ever plug a number into a function and we can't get a real number as an output, then we know there's some sort of domain issue. The most common occurrences of this happen with dividing by 0, negative square roots or other even indexes, and negative logs. We won't worry about negative logs today, but we've already seen examples of the first two. There are two ways to write domains and ranges: interval notation and set notation. Interval notation uses parentheses or brackets to imply where the function is defined. Set notation uses sets to say explicitly where the function is or isn't defined. Take a look at this table for a few examples. The parentheses indicate that the endpoints are not included in the interval. You'll use these with not equal to scenarios and greater than or less than inequalities, as well as with all positive or negative infinities. The brackets indicate that the endpoints are included in the interval. So you'll use these with greater than or equal to or less than or equal to scenarios. That vertical bar in the set notation after the first value is read as such that. So in the first example, we would read the notation as x such that x is not equal to 8. The symbol that looks like a fancy E indicates set membership and means is an element of. In the last row of the table, the statement y with the fancy E and the R means that y is an element of the set of all real numbers. To show that in interval notation, we say from negative infinity to positive infinity using parentheses. It's really hard to identify the range of a function without a complete graph. So you can do this by plugging in a lot of x values, but since most courses are going to allow you to use a graphing calculator, this is what we'll continue to do to figure out the range, along with the knowledge of what inputs we're allowed to plug in. Example 3. identify the domain and range of each function using set and interval notation. Okay, g of x equals 1 over x minus 5. We know from our previous example that fractions, we have to be careful, and the denominator can't equal 0. So I'm going to take the expression that's in the denominator and say that x minus 5 can't be 0. And when I solve for x, that tells me that x can't be 5. There's my domain. I know I can plug in other positive numbers, other negative numbers, fractions, but the only thing I'm worried about is the denominator being equal to 0, and that's only going to happen when x equals 5. So my domain for this function is going to be x such that x can't equal 5, or everything other than 5. So using interval notation, that's going to be everything from negative infinity up to 5. I'm going to use this U symbol, which stands for union, and then everything from 5 to positive infinity. To figure out the range, I need to look at a graph. So if I plot y equals 1 over x minus 5, I get this picture. We can see from the graph that plugging in everything except for 5 are going to result in y values of everything except for 0. So there's a vertical asymptote at x equals 5, which is where the domain is undefined, and a horizontal asymptote at y equals 0. This means that y can be anything but 0. So we can write the range as y such that y can't be 0. And in set notation, in interval notation, everything up to 0, but not 0. Let's try another one. H of x equals the square root of x plus 4. We have an even radical, so x plus 4 can't be negative, which means x plus 4 has to be greater than or equal to 0. If I solve that for x, I get x is greater than or equal to negative 4. So as long as I plug in numbers that are negative 4 or greater, I'm not going to have any issues. Well, how do we write that in set and interval notation? So in set notation, that's going to look like x such that x is greater than or equal to negative 4. And in interval notation, that's going to look like a hard bracket, negative 4, all the way up to positive infinity. I'm using a bracket instead of parentheses to imply that negative 4 is an acceptable input. And again, to get a sense of the range, we need to refer to the graph. So if I graph y equals x plus 4, I get this picture, and I can see that when we have x values that are greater than or equal to negative 4, this is going to result in y values greater than or equal to 0. So therefore, my range can be written as h of x such that h of x is greater than or equal to 0. And in interval notation, that looks like a bracket with a 0 to positive infinity. Again, I'm using that bracket to signify that 0 is an acceptable solution. Now it's your turn. Pause the video and try this next one on your own. Example 4. State the domain and range of each function below using interval and set notation. Let's see how you did. So based on what I can see in the graph, x is defined everywhere, and so is y. So it looks like I can plug in any value I want for x, and it looks like when I plug in x values, they get more and more positive. Or sorry, more and more positive, I get more and more negative y values. And when I plug in x values that are more and more negative, I get more and more positive y values. So in this case, my domain is x such that x is an element of the set of all real numbers. Or I can write that as negative infinity to positive infinity. And similarly for my range, y such that y is an element of the set of all real numbers, or from negative infinity to positive infinity. All right, one more to try on your own. Pause the video, give it a shot, and then come back and see how you did. All right, so y equals the square root of 8 minus x over x squared. So there's a few things we have to worry about here. We have a fraction. So the first thing I'm going to worry about is that the denominator can't equal 0. So if x squared can't equal 0, that means x can't equal 0. All right, I also have to worry about the values underneath the radical being negative. So I'm going to set 8 minus x being greater than or equal to 0. I'm going to subtract 8 from both sides, and then I'm going to divide by -1, which means that's going to reverse my inequality, and I'm going to end up with x is less than or equal to 8. So I have a couple of rules for the domain I need to follow. X can't be 0, but x has to be less than or equal to 8. I might need to look at a graph to figure out a little bit more about my domain. So let's go ahead and do that. Okay. So for this particular graph, I can plug in numbers that are going to be between 0 and 8, but not 0. And I can plug in numbers that are less than 0, and I'm still okay. So how do we write that as a domain and range? Well, we're going to be in a couple of pieces. So let's start with set notation. So I want to say x such that x is less than 0, oops, or x is between 0 and 8, but not equal to 0, but 8's okay. So that's going to look like this. It's kind of a long domain, but that's what we have to work with. I can also write it like this. Everything up to 0, but then also everything between 0 and 8. Include 8, don't include 0. Okay, that's a lot. Now, notice from the graph that when I plug in those domain values, I'm only getting y values that are greater than or equal to 0. So when I plug those numbers in, my range is either y such that y is greater than or equal to 0, or I can say 0 to positive infinity. I'll be able to get 0 as an output if I plug in x equals 8. So underneath the radical, I would have 8 minus 8 is 0, square root of 0 is 0, and then 8 squared is 64, but 0 divided by 64 is still 0. So I am able to get 0 as an answer. I just can't have 0 in the denominator. This is a totally made up function. Just wanted to do an example problem that wasn't like a normal radical or function that you would typically see. For more step-by-step guided practice, check out the accompanying behind the scenes video for this episode. Remember that developing a solid understanding of math takes time and practice. If you like what you saw today, please like, subscribe, and tell your classmates. Thanks for watching. I'll see you after class.